Good afternoon, everyone. Welcome again to our workshop. Let's continue with our program. Thank you very much for your presence. So the first lecture, plenary lecture of this afternoon session will be given by the Professor Felipe Linares from IMPA. It's a pleasure for me to introduce him. Felipe is a full professor at IMPA in Brazil. He works in nonlinear dispersive equations and harmonic analysis. He has many papers. Felipe also has formed several master and PhD students. Joined with Gustavo Ponce, they have a very nice book, Introduction to Nonlinear Dispersive Equations. Felipe is one of those responsible for the dissemination of the dispersive equation field in Brazil. It's a great pleasure to have here Felipe. Thank you for accepting our invitation. So Felipe will talking about the Cauchy problem for the L2 critical generalized Zk equation in dimension 3. Thank you, Felipe.
Okay, thank you, Carlos. Thank you very much for the introduction and for the invitation to participate in this workshop. I also would like to thank you to Juan Limaco and the other organizers. So today I would like to talk about this recent result in collaboration with Joao Pedro Ramos. So he was a student here for the master program, and then he got a PhD in Germany, and now he's a postdoc of in ETH in Zurich. Okay, so I'm going to talk about the initial value problem associated to this equation here. So it's a Sakharov-Kuznetsov equation. So you will see that the power is not so common power, and for the nonlinearity is 1/7. So that it makes perfect sense for any real function. And then what we are interested is, well, this has a nice property. It's the critical equation for this family of PDE, of nonlinear dispersive equation, in dimension 3, right? So the plan of my talk is as following. I'm going to give you a motivation for the study of this initial value problem. And then I will talk about the main results and some remarks. And then I will give the idea of the main result. Okay, so I'm going to tell you several results, but I will be focused only in the proof of the local well-positiveness result for the initial value problem that I showed before. Okay, so this equation that I just wrote before is part of this family, okay? But here is what is called the generalized Sakharov-Kuznetsov equation. You got this nonlinearity here with power and integer number, right? And this equation can be considered physically at some meaning, right, when k is equal to 1, and in dimension 2 and 3, all right? So the equation is not only an equation that is nice, but it's actually a model, right, in plasma physics. Okay, so Sakharov and Kuznetsov in 1974, they came out with this model for long-wave small amplitude limit of the Euler-Poisson system in cold plasmas. Okay, and it was a formal derivation of the equation, and then together with David Glantz and Jean Clouseau, we justify rigorously the derivation of that equation. Okay, so physically it makes sense, right? And either in dimension 2 and 3. All right. So the equation that we the generalized KDB equation, the generalized CK equation, is not completely integrable, right? So this is, we cannot use inverse scattering in order to solve the problem. But anyway, we have some quantities that are invariant by time. Okay, so we have the F1 norm, so we have the L2 norm, it's important. And this one that involves first derivative, right, that combined with this can be useful in order to get some a priori estimates and then extend solutions locally to global solutions, right? So these are one of the motivation to study the initial value problem, at least in H1, hopefully in L2, we don't know. And then we can also see this CK equation as a generalization of the Korteweg degrees, right? So some people doesn't know about the physical meaning that is completely different from the physical meaning of the KDB. The KDB, you can see, is just a model the propagation of nonlinear waves in shallow water, and CK is a model in plasma physics. And another generalization of the KDB equation in 2D and 3D is also possible, is the Candoset-Pesbiatvili equation, or KP equation, right? And it looks quite different from the CK equation. And sometimes if you think on the CK equation and you would like to talk about local well-postness in very low regularity spaces, you may think that it would be easier to deal with CK instead of the KP equation. Of course, I had to say the KP2 equation, right? Where many results were obtained in very low regularity spaces, right? And then here we have and also you can see the differential operator associated to CK is local, and for KP we don't have this is not local anymore, right? So we have this antiderivative. This is written like this. Okay, so here I say I'm going to talk about the local well-postness, and I want to make clear what is in what sense we are talking about local well-postness. So we have this initial value problem, right? And then we follow, as always, the Kato notion of well-postness that not only includes existence, uniqueness, and continuous dependence, but also the persistence property that is the following. If we started with some initial data in some functional space, the corresponding solution describes a continuous curve in X. Okay, so in other words, U is continuous from 0t into this space, the functional space. Okay, so if this property satisfies for any time, right, we say that the initial value problem is globally well-posed. And in general, when we are talking about nonlinear dispersive equation, the natural space to work is the Sobolev space in base 2, right, HS, where S is okay, we have this problem. Everybody in PD knows this definition, right? Okay, it's good for the students. All right, so when you are going to work with the initial value problem, so you would like to know where do you have a chance to get this property, right? Where to prove this local well-postness, right? Okay, so in order to guess that, okay, so you may say, well, I have this conserved quantity in L2, another conserved quantity in H1. Okay, but then there is this method that you can use in order to, depending on the structure of the equation, right? You can guess which would be the low or the less regular space where you can obtain local well positive, right? And so this is an scaling argument. And you started with the initial data in HS, right? And then you consider the corresponding solution. Then you can have this family of new solutions with this initial data, right? And then what you try to see is when you can have derivatives that are invariant, right? By lambda. Okay, so the only way to get invariance here is to set S equal to the dimension over 2 minus 2 over k. Okay, this number over here. And then morally, we have a local well positioning anytime we expect to have local well positioning for S greater or equal than Sk, this number here. If Sk is smaller than this number, one can argue and say that the continuous dependence doesn't work in the case that S is less than Sk, in the sense that we mentioned before. Okay, so we expect to have local solutions if S is greater than this number already. Okay, so next I would like to tell you what has been done regarding local and global well positioning for CK equation, right? And what is the motivation to work with the equation that I showed in the first slide? Okay, so this local well positioning theory started with the work of Fluminense in 1995, where he proved that this problem is local well pos in HS S greater than 1, and he considered S an integer number. And the method used the smoothing effects, right, of the equation, right, and the solution of the equation, and then contraction mapping principle. Okay, this is based on what Kenny, Ponce, and Vega did for the first time for KDB equation. And then in 2009 with collaboration with Ademir Pastor, we extended this result to any data in HS S greater than 3/4, right? And we don't have any S is real greater than 3/4, and we were inspired by the work of Kenny, Ponce, Vega for KDB in the contraction mapping principle paper, right? So we have a local well positioning in that space. Of course, if you say, well, this is optimal or not, you have to go and look at here, right? So you start here in dimension 2, okay? And k equal to 1, so we are far from the optimal, right? So it should be S equal to -1. Okay, so people try to get better, and then there is a result that was obtained independently by Molinet and Pilot and Grunrock and Herr, right? And in that case, they use the Fourier restriction method, one using the bilinear streaker estimate, the other one using the Bourgain method directly. And they obtain local well positioning in HSS greater than 1/2, right? So the results at this point are all global if S is greater or equal than 1. Okay, so local well positioning for S greater than 1/2. So recently, Kinoshita obtained the best possible result for the using contraction principle, right? So he proved that if S is greater than -1/4, then the local well pos is set in that space and larger than that, right? And what he did was try to look at the bilinear estimates that were already in the paper of Grunbrock and Herr, probably, and he used a beautiful and sophisticated method in order to get the result in S-14. Okay. Of course, this result implies that in particular you get global solutions in HS S greater or equal than 0. Right? You can also see what happened. So, because we are interested in the generalized case, what happened for powers greater or equal than 2. Okay. So in this case, again, I mentioned what is the best possible result, or the largest space that we can have a local result. Right? And then there are several results here. I can say that the sharp local results are obtained by Ribot and Bento for the case k greater or equal than 4. And then Grunbrock proof in the case k equal to 3 is greater than 1/3, right? So he just needs 1/3 here. And for the case k equal to 2, k equal to 2 says that L2 is the largest possible space where you can have local well poses, right? So either in that case, k equal to 2, the best possible result is S greater or equal than 4. Okay, so Ribot and Bento prove the result for S greater than 1/4, and Kinoshita proved that this is the best possible result, right? S greater or equal than 4. So he proved S equal 1/4, and he proved that you cannot be better than that if you want to do the contraction mapping principle. And regarding global well posedness, in those cases, we have, for instance, in the case of k equal to 2, right, that you can have global solutions for S greater than 3/4, and it was proved by Mataraye, Gustavo Farah, and Speltrana Rudenko in 2020, right? Okay, so for the index below 1, so we have global well posedness in H1, right? But there is some restriction on the size of the data, okay? So for the 3D case, in k equal to 1, we have a result by Ribot and Bento. And I just have to tell you that the method that we are going to present today is just a variation of the method of Ribot and Bento in the 2D case and the 3D case. So they show local well posedness in H1, right? In HS greater than 1. There is a result in collaboration with Jean-Claude So. It was the first one that we proved local well posedness in this setting. And then there is a result by Molinet and Pilot, proving that this local result can be extended globally, right, without going into the in the conserved quantity. And last year, Herr and Kinoshita proved that they can do better than this, right? And they go to S greater than -1/2. So in particular, they have global well posedness in L2, right? Or above. Okay, for k equal greater or equal than 3, let me see if I jump. Okay, so next. K greater or equal than 3 in dimension 3, Grunbrock obtained local well posedness in these spaces, right? In HS with S, these indices here. And for the case k equal to 2, it was addressed by Grunbrock and Kinoshita, and the best result they can obtain is S greater than 1/2. All right. And additionally, Kinoshita could prove that this result can be extended globally for S greater or equal than 1/2, right? And then again, you have to be careful with the size of the initial data. Okay, it should be for small data. Okay, so, and coming back to what is the problem when, for instance, in the case k equal to 2, dimension 2, right? In the case k equal to 2, dimension 2, you can call the CK, the generalized CK, as a modified CK equation, right? And you can see that the critical space, meaning that the L2, if you want to prove something in L2, you cannot do it, right? The best result is S in HS, S greater than 1/2, right? Than 1/4, I think. Okay, but still, you can see if the solution, the global solution, are for any data in H1, for instance, right? And then you combine the conserved quantity in L2, and this conserved quantity that combined with the L2 gives you a priori estimate in H1, right? But then, since this is okay, this is just, you measure the L2 with this norm, then the only thing that we need in order to get a priori estimate is to control this one. Okay, so in order to do that, you use a Gallardo-Guillenberg inequality, right? A sharp one, and that sharp one inequality gives you this here, right? This estimate, where Q, I don't know if you see that, is the solution of that stationary problem, right? So if the initial data in L2, right, in the L2 norm is smaller than this L2 norm, right? Then you can pass this to this side, and then you have an a priori estimate. Okay, so you will have a solution for this problem whenever the initial data in L2, right, satisfy this condition. Okay, so recently, Farah, Holmes, Protein, Qualin showed the solution of the initial value problem associated to the 2D L2 critical equation in 2 is blow, sub, infinite, or infinite time. Okay, so you will see that this is a critical in the sense that you have a problem, you can extend the solutions to any initial data in H1. The initial data in H1 has to be with the L2 norm satisfying this condition. If this condition is not satisfied, then the solution may blow. Okay. Okay, so what is the situation in the 3D case, right? So if we go back to the number sk, right? The sk was dimension over 2 minus the power over 2. And then what happened is that if k is integer, you don't get the L2 as a possible space to have a solution, right? Or to deal with the initial value problem, right? And then the natural question that arises whether can we have a meaningful equation generalizing the CK equation, right? Where we can expect local well-postedness in L2. Right? So instead to do the scale with k an integer number, what we do is just, well, we let k to be a real number, right? So just vary through the reals. And then we found that the power should be the one that we have in the first equation. It should be 7/3, right? And 7/3 is fine. Okay, we don't have any restriction in the values of the solution u, right, or the function u, and then we can consider this as a critical equation, right? And then it's not only because of the L2 should be the largest space where we have a solution, but also because of the same argument that I've showed you before about global well-posedness. It also happens in this case. Okay, so you may have a solution in H1, right? But the initial data has to be in the L2 norm below the stationary solution associated to that equation, right? And that's and the stationary solution were already studied by Anne de Boer, and she showed that if k is less than 4/3, this stationary solution or solitary wave solution, if you would like to call them that way, are stable if S is less than 4/3, okay? And they are unstable if K is greater than 4/3, right? And then in the case K equal to 4/3, there is no decision if you have there is a criteria to use, but then if K is equal to 4/3, you don't have either instability or stability, and then the conjecture is just that in that case is unstable. Okay, so with this, at least these three motivations, right? We try to see if somehow we can prove local well-posedness for this initial value problem one, right? So I show you a lot of results, and there are several techniques that we can use in order to say something, to give some positive answer to this question of local well-posedness. However, we need to introduce some new ideas in order to get the local theory, right? Okay, so now I'm gonna tell you what we got. So we got a local report, a local well-posed result in HS for S between 3/4 and 1. Okay, so okay, it's nice because we got a local result, right? In this space, we got the persistence, intersection, one space I'm going to show you in a few minutes. And then we have the existence, the uniqueness, persistence, and we also have that the application data solution is locally Lipschitz continuum, right? Okay, this is because we are using the contraction mapping principle. All right, so but then what happens? Well, in this case, the method that we use is the method by Ribot and Vento, where they use paraproduct decompositions of the power, in this case, U to the k. But in our case, we are in the middle of these two results, right? Like you are in CK as in 3D at Ribot and Vento, and K equal to 2 of Room for in K in dimension 3, right? So in order to handle this power, we are going to introduce an almost paraproduct decomposition, right? And then it allows us to use the Picard iteration and obtain a local result in 3/4, right? Then the constraint there is because we use the linear estimates right? Or estimates from the linear solution of the problem. And one of these estimates are the maximal function estimates. And the best we can do is to take s equal -1. There is a restriction there, and this estimate is sharp, so we cannot improve that. Nevertheless, we try to see if we can do something better, because we, at least if we hit H1, we may try to extend the solutions globally, right? And then, well, we came out with this idea of an almost well-postness result. And this can be done in S between 1 and 2. And what we mean by that? Well, we have a problem with, we can obtain a local solution. So we prove the existence of that solution. But then we cannot prove that the continuous dependence on the initial data. Okay, so we can refine the estimate that we have. So is in the paraproduct that we obtain, the estimate involved in there. Instead to have a gradient, we can put a Laplacian, but anyway we cannot do better than what I wrote here. So we are using the Duhamel, but the Duhamel term is just 1/3 order continuous, and this doesn't allow to use Picard iteration, right? Okay, so what we do is, well, recently there are these results, like, so you deal with smooth solutions, and then you obtain some a priori estimates, right? And these a priori estimates solve your problem, right? And so this is what we did. So we take initial data in HS for S in between 1 and 2, right? And for each R here, we got a solution, right? In this space, intersection this space, right? So what, well, I didn't say correctly what almost well-postness is, but you have existence, we have uniqueness, and the solution is regular as the initial data, okay? But there is no continuous dependence, okay? So if I start in H1, the solution is in H1, but I don't have any connection. The solution doesn't depend continuously, it depends continuously on the initial data, all right? But we maintain the regularity, and that's nice, okay, for our purpose. So when you have this lemma that I mentioned before, right? You got solutions, and now you want to have a solution for any S, right? So what we obtain is the following. So we get this solution for the lemma 1, right? And this solution belongs to this space. So it's an infinity here, intersection, this space that is, again, the intersection of all the spaces given in lemma 1, right? And then the norm is given by this measure, right? So we'll measure the integral from phi 6 to S of all the measures, of all the norms in the lemma, okay? And then the only thing that we see is that if we have this small enough, this solution is small, but this doesn't tell us that this is the continuous dependence result, all right? What is good is that if we start in HS, right, between 1 and 2, the solution of the initial value problem, 1, belongs to this space, okay? I haven't told you what is the space, but you still are in this space, Okay. So in particular, your continuous intersection this space, right? But we still don't have a continuous dependency. All right. So what we have here is a local well postness, right? In 3/4. In that case, 3/4 So we have 21 guarantees that the data solution map is continuous, right? But we don't have for greater than or equal than 1, we don't have continuous dependence, but we don't lose regularity. Okay, if we are in between 1 and 2. And then we can say that we have an existing result, right, between 3, 4, and 2. Also, if S is greater than 2, we can also prove some result, the usual one. But then we can see that the scaling is just S equal to 0, that is L2. So we are really far from the chart, right? Oh, anyway, we can prove that we can now have a continuous dependence in L2, right? Using the same argument that we implemented in the case, into the case for the critical CK equation, or the modified CK equation, right? Okay, so but then we have some result in H1, and we would like to say something about global solution if that is possible. Okay, so the first thing is to make sense of the conserved quantity that we have, right? And this is the first task that we need to do. Then, if we have this conserved quantity meaningful, right? Then we can extend solutions, and then our result for say that we can do it for initial data is small, right? So the first thing is that if we get any solution here, any data in HS in R3 in this interval, right, of regularity, so we got a solution that is here, right? And we know that it exists and that is unique. And then we prove that this is satisfied. Solution in these spaces satisfy that the L2 norm is invariant. So that makes sense. And we also prove that if S is between 1 and 2, this also makes sense, right? For the solution that we have. Then our second theorem says that yes, we have global solutions if the L2 norm is sufficiently small. All right, so we are in a good track. So we would like to have H1 solutions in the sense of Kato. Okay, we don't have it, but still we have global solutions in this sense, right? And then the last result has to do with something that has been studied since Carlson, as the following question. So you have Schrödinger operators, right? And then you ask for which S real does it hold that this limit is realized almost everywhere in X. So you have pointwise convergence, right? And then Carlson showed that this happens in the case n equal to 1 in H1/4. Okay? So since then, there are many works regarding this kind of questions, right? and then not only for the linear problem, but also for the nonlinear problem. So in that case, we were inspired by the recent work by Copan, Luca, and Staffelani, where they were dealing with some Schrodinger equation, right? And then we prove that if S is greater than 3/4, for solution of the complete generalized or critical L2 CK equation, we have this property. And this is combined, we combine the technique of Copan, Luca, and Staffelani, and the 4 maximal function estimate of Grunbrock. Okay, so this complete the set of results that we prove, right? Okay, so I have 10 minutes. Carlos?
9 minutes.
Okay, perfect. Okay, now I will be very fast, right? Because this the technical part you don't want to see all the computation, but I just want to tell you how the things go. Okay, so as I told you previously, we are going to use almost parallel product decomposition, so we need to use a little Pali decomposition, right, of R3, and these are the definition here. And the important thing is that if we have this little Pali decomposition, we have also a characterization of the Sobolev spaces using this, right? So we can have HS using the little Pali decomposition I just wrote. All right. So you can now write the norms of, I mentioned before, the X, ST, and they are coming from some properties of the solution of the linear problem. So it's the Sobolev norm, the smoothing effect norm, the maximal function estimate norm, and the Stricker norm, right? And then with these 4 norms, we create the space that we talked about all the time before. This is the XST space, combining all these 4 estimates. And we observe that if K is greater than 4 in the projections, right? So instead to use this one here, we can use this norm over here. Okay, so you put in clearly what are the derivatives that you are using every time. All right, so, and those names as I gave to the norm before are coming from the linear estimates associated to the linear problem, right? And the first one is regards to the Catton smoothing effect, that is said that solution of this problem, they gain one derivative in this space, right? Then you have the maximal function estimates. So you have L infinity in Y and T. Y here is for the last 2 variables, and X is only for the X variable, right? And then this estimate here is sharp, so you cannot get better than 1. Okay, and this is the instruction that we have in the method that we are using. And then if you do the projection, you can obtain this estimate, right? So this was done by Ribot and Bent. Then we have L2, L4 Stricker estimates, and it was obtained by Grunbrock, right? And we are going to use it here too. And then, because we are doing the contraction mapping principle, we are using the Duhamel formula. We need these estimates, right? The estimates in the Duhamel term. right? And so you have the smoothing, this is the dual of the smoothing effect. You have the smoothing effect norm, you have the maximal norm, maximal function norm, and then you have the Stricker estimate L2, L4, Stricker estimates in L4, right? So you can notice that all of these estimates finish in this space, L1 in X, L2 in Y, T, and then the same is here, right? So you can estimate all of these norms and finish with this quantity at the end. Okay, so as always, you try to prove that this operator has a fixed point, right? And then, because of the linear estimate that we obtain, or the estimate for the linear problem, we have this. Okay, so there is no problem with the linear part, and we are only concerned with the nonlinear part. All right. So instead to go and estimate this, we can start it with this, and then if we do this, that term implies this one, of estimating this estimate. Okay, so we can apply all the propositions that we have before, especially proposition 4 and 5. Okay, so if we do that, the nonlinear term will end up here, right? So you have L1 in X, L2 in Y and T, and we are now in the blocks. Okay, so we had to add together all the blocks and see if we can estimate this. Okay, so the idea of Ribot and Bento, right, was to use this decomposition, right? So you have the projection. So instead to have delta k, we have the sum of delta k's here, sum of delta k's here, right? Sum of delta k here. So you have a very nice and neat formula, right? And with that, you can do the estimate. So in our case, we need to have, this is the key of everything here for the local well postness, one estimate for this term here, right? And what we did was to find a formula, this almost paraproduct for this difference here. Right? So we started like approaching just an approximation of what is this, right? With the projections. And then we rewrite better this difference here, right? Using the mean value theorem for the integrals, right? So we do this linear combination here, this linear combination here. And then using the property of projection and all that stuff, we rewrite this a couple of times. And finally, we get a nice formula to start with. Okay, so if you estimate this part, you already have the difference of u minus v. And if you control all this part here, so you already have the difference of u and v, right? And then this is, well, from now on, you have to do computations and estimates, and then you have to do Minkowski, Young, inequality, Holder in the blocks, right? Right. Some parts in the blocks, some other part is the norm in the complete space, right? So we have to differentiate when we have low frequencies and high frequencies, but still in doing this again, we are going to use Young inequality and Holder several times. We can obtain an estimate that look like this, right? So this is very helpful, right? It's nice to keep going. And then we analyze high frequency, low frequencies, and try to finish to close these two estimates, okay? So again, we interpolate, for instance, Sobolev and Stricker estimates in order to control these guys here, right? And then we got a nice inequality there. Then when we try to compute this guy, well, now we have to pay with something here, right? And then we can control this estimate if we know how to control imposing some condition in this power. So we have to do the same for well, we keep saying that if S is larger than this number, right? So we have some room to do more estimates and then finish with this part if S is larger than 3/4. And the other term, this one over here, the low frequencies, again, we started to do estimates and then we use several times the discrete Joule inequality, right? Like here. And then we finish with something like this. And finally, okay, we have this condition, the whole condition here is that we cannot go further H1, right? But then we got the lemma, and with that lemma we are done, right? So basically we have the application that we want to prove that is a construction. And then with the lemma, we can close the estimates and then obtain a local result in 3/4 and 1. Sorry, well, it was my intention to pass very fast the technical part because it's kind of painful to tell you any step involved, right? And then I'm going to finish. Yes, thank you for your attention, okay, and to be here. Thank you very much.
Oh, thank you very much, Felipe, for the nice talk. Very nice. So, someone has questions or comments? You can open the microphone or write on the chat.
Carlos, Luis, can I ask a question to Felipe? Can you hear me?
Yes.
Felipe? Hi. Yes. So, yeah, I have a couple of questions. So, regarding theorem 5 that you show, you say that you have some pointwise convergence, right? So, this result is in dimension 2 and 3 or just 3?
I think you can do it in 2. Okay. We did it in 3 because it's probably we did it in both. We mentioned that we can do it in both, right? Okay.
Right.
Okay, so we did it in 3 dimensions, but I think in 2 dimensions it may work. Okay.
Okay, it also works. Okay.
Yeah, depending on the maximal function that you got available in that case. Because the method of Copan, Luca, and Staffelani is very nice because you can follow step by step and the right ingredients there.
Yeah, this paper is about what kind of equation? Schrödinger or KdV or?
It's a Schrödinger equation with power that is not necessarily an integer, right?
I see.
Okay.
Very nice. Great. And also, there is also a result, I forgot to copy the name of the result, where you say that you have global solutions in H1 for small data, right? You say that if the 2 norm is small, then you have global solutions in H1. So can you say something about how small the data should be?
No.
Not related to the Gallardo-Nirenberg inequality or this?
No, because we actually we do that by hand, right? By hand, and I said like when you do the first time, it's
okay.
you remember, Luis, when you do the first time, they say, well, if this is small, then we can close it. Right? But of course, the conjecture is it has to be the stationary solution associated with the equation, right? So, but we don't have continuous dependence, so we don't know. Okay, but it should be that one. Okay.
Okay. Thank you.
Okay, a pleasure.
I would like to thank again Felipe for the excellent talk. Thank you very much for accepting our invitation.
Thank you.
Thank you, Felipe.